All right, mates, here we go again. It's common knowledge that malicious payloads can be purchased and deployed anywhere from $150 to $800, depending on the sophistication involved. These payloads, once run on a remote server, can create a reverse shell, seemingly like magic. However, the real value lies not in the acquisition, but in a deep understanding of payload creation from a multi-layered perspective. This knowledge is crucial for predicting behavior and evasion tactics against detection mechanisms like Windows Defender or other Endpoint Detection and Response (EDR) systems. It's important to note that all our tests are conducted in isolated labs and controlled environments. Caution is advised for those conducting their own research. Let's start from the beginning. Imagine we've created a Windows payload using MSF Venom on Kali Linux. You've meticulously crafted this payload, incorporating encoders such as Shikata Ganai, a polymorphic XOR additive encoder. Congratulations, you have just created your first little baby, a copy of your own intentions. It's a given that a malicious payload, when using raw shellcode, will invariably trigger alarms in Windows Defender. However, as discussed in our previous video, employing encryption techniques like XOR and its polymorphic variants, AES and RC4 can aid in evading Windows Defender's real-time protection. This method effectively bypasses the static analysis engine of Windows Defender. An interesting observation is made when a payload encrypted with XOR is outputted to the console via Visual Basic without execution. The output sometimes contains readable characters. These characters appear less random compared to those encrypted with techniques like AES or RC4, sometimes even revealing repetitive patterns. That's why we previously pointed out XOR being a weak encryption technique. Payload obfuscation, IPv4, IPv6 fuscation. With a solid understanding of payload encryption established, this module shifts focus to payload obfuscation as an alternative strategy for evading static detection. Unlike encryption, obfuscation modifies the appearance of code without altering its functionality, providing an additional layer of indirection. This versatility is crucial for malware developers striving for unpredictability. Through this discussion, we introduce advanced obfuscation techniques exemplified by their application in scenarios such as the Hive ransomware. Important note, the code examples provided in this and subsequent modules should be compiled in release mode to ensure proper functionality, as compiling in debug mode may lead to operational issues. Understanding IPv4, IPv6 fuscation. IPv4, IPv6 fuscation represents a novel approach to obfuscation, transforming shellcode bytes into IPv4 or IPv6 address strings. This technique leverages the structural characteristics of these addresses for disguise. For instance, using the initial bytes from an MSvenom x64 Calki shellcode, we can illustrate the conversion process for both IPv4 and IPv6 fuscation. IPv4 fuscation. Given that IPv4 addresses consist of 4 octets, this method repurposes 4 consecutive bytes from the shellcode into an IPv4 address. For example, the hexadecimal bytes FC4883E4 translate to the IPv4 address 252.72.131.298. IPv6 This method extends the concept to IPv6 addresses, which comprise 16 bytes, forming a single IPv6 address without requiring decimal conversion. The same shellcode segment thus becomes the IPv6 address FC4883E4, F0E8, C00, Y0, 41, 51, 4150, 5251. Implementing IPv4 obfuscation. Implementing IPv4 obfuscation involves generating IPv4 addresses from shellcode, with each address corresponding to 4 bytes of the shellcode. The shellcode length must therefore be a multiple of 4, and additional padding may be necessary. The generate IPv4 function exemplifies this process, converting 4 shellcode bytes into an IPv4 address string using sprintf. It's crucial to note that this section focuses solely on obfuscation techniques, with deobfuscation covered subsequently. IPv6 obfuscation implementation and deobfuscation. Similarly, IPv6 obfuscation requires the shellcode to be in 16-byte increments. The deobfuscation process for both IPv4 and IPv6 obfuscation reverses their respective obfuscations, converting IP address strings back into byte sequences. This is achieved through entopy functions artCharlIPv4 string to address A and artLIPv6 string to address A for IPv4 and IPv6, respectively. Deobfuscating IPv4 obfuscation payloads. The process involves converting an array of IPv4 address strings back into the original byte sequence. A buffer is allocated based on the array size, with each IPv4 address contributing 4 bytes to the final payload. The RTLIPv4 string to address a function plays a pivotal role, parsing each address string into its binary form and populating the buffer accordingly. Payload obfuscation, MACFuscation. Now this is very interesting, an obfuscation technique that transforms shellcode into MAC address representations. Drawing parallels to the previously discussed IPv4, IPv6 obfuscation, MACFuscation leverages the format of MAC addresses to conceal the original code, offering an innovative approach to evade detection mechanisms. MACFuscation implementation. The process for implementing MACFuscation follows a methodology similar to that of IPv4, IPv6 obfuscation, with the distinction that a MAC address consists of 6 bytes. Accordingly, the shellcode must be divisible by 6. Padding may be applied to the shellcode to satisfy this criterion, ensuring compatibility with the MAC address format. Deobfuscating MACFuscation payloads. The deobfuscation phase for MACFuscation involves converting MAC address strings back into their original byte sequences, effectively reversing the obfuscation process. This crucial step utilizes the NTDLL API function, which interprets a MAC address's string representation and returns its binary form. Through this function, obfuscated payloads camouflaged as MAC addresses are decoded back into executable shellcode, ready for their intended operation. Payload obfuscation, UUIDFuscation. This is a sophisticated obfuscation technique that transforms shellcode into a universally unique identifier, UUID, string format. Unlike other obfuscation methods, UUIDFuscation employs a 36-character alphanumeric string commonly used to uniquely identify information, offering a unique blend of complexity and stealth. UUID structure. The structure of a UUID comprises 5 segments of varying lengths, typically represented as 801B8E, F0832004ADA, BB1341EA1C86B87. This format integrates both alphabetic and numeric characters distributed across these segments, providing a versatile foundation for obfuscation. Converting shellcode into UUIDs. The process of converting shellcode to UUID strings deviates from simpler obfuscation techniques, primarily due to the endianness involved in the conversion process. For instance, the shellcode sequence FC4883, E4, F0E8, C0000, 41, 51, 41, 50, 52, 51 translates into the UUID E48308, FCE8, F0, 0, 0, 0, 0, 415, 4505, 2 of 1, not FC4883, F08, C0, 0, 0, 0, 415, 115, 251 as one might initially expect. Little endian conversion. Segment 1, FC48, 83 E4 is reversed to become E4 83 48 FC. Segment 2 E8F0 is reversed to become F0 E8. Segment 3 C0 00 is reversed to become 00 C0. Big endian conversion. Segment 4 00 00 00 remains unchanged. Segment 5, 41, 51, 41, 50, 52, 51 remains as is due to its direct translation, UUIDFuscation implementation. For effective UUIDFuscation, the shellcode must align with the 16-byte structure of UUIDs, mirroring the requirements of MACFuscation. This ensures a consistent and coherent transformation of the shellcode into the UUID format. Should the original shellcode not meet the 16-byte multiplicity, padding may be employed to fulfill this structural prerequisite, akin to the approach in IPv6 fuscation. Remember, mates, the main theme here is unpredictability. In the realm of cybersecurity, particularly in the development and deployment of malware, the ability to remain elusive and unpredictable is paramount. By the way, if you enjoyed this content and would like to support us, our donation links are in the description of this video down below. I'll see you guys in the next one. Stay safe and alert out there.